Welcome to the what month is this? The May TechNet. Um, as those of you who are usually here know, this is a session that's one of three different types of programs we've got in the club. The Wednesday night sessions are usually much broader lecture type sessions over a wide range of topics, and then Tech Saturday is kind of get together, hands on type of material, and the goal of the TechNets really is to be able to work with your stuff when you're home and try things out with your own equipment, which you couldn't do at a Tech Saturday because you don't have it all with you. And so that's kind of the forum that we've tried to have for the TechNets. We also had a lot of discussions recently about what the topic material should be, and it's kind of varied from the more traditional introduction to FT8 type stuff to some of the stuff Mark was talking about, things like making printed circuit boards and stuff like that. So that's one of the challenges that we've got is in figuring out what we're going to do. But tonight we have the pleasure of Jim Wright presenting for us. Jim, as everybody knows, is one of the best presenters in the club, and when we're doing this whole session on antennas for these 2 months, I twisted Jim's arm into coming in and reprising a little bit of the Tech Saturday session that he did a couple of months ago. But with us sitting at our computers at home, we can probably do this stuff a little bit better. So I asked Jim if he would just fool around a little bit with the antenna that we built on Saturday. We had 14, 15 people out there working on those things, which was really great, and he agreed. So Jim, take it away, and thanks very much for doing this.
All right, thank you. So I see we got 14 participants on here. As John was kind of introducing, this is a bit tech. It's if you were at the last club meeting on Wednesday, we got to hear Spencer Webb, W2 Sierra Whiskey, talk about irreverent antennas, and he gave a very nice high-level overview of some of the general ideas about how antennas might work and radiate. Then there was this Tech Saturday, which we'll touch on a little bit more. And then coming up at the next Tech Saturday, so that would be next month, Ed Fong, WB6IQN's dual band antenna build. That sounds pretty interesting. Well, one of the things that I like a lot is a field day and whatnot. I'm just going to put this slide up temporarily. In case you haven't downloaded the software in advance, we're going to actually let everyone have a chance to try out running this antenna modeling software. And we're going to take a look at a couple of models. What is what is an antenna modeling software? And the web page for 4NEC2, which is one of them, kind of describes what this is all about. In short terms, the United States government taxpayer money helped fund this work to do some analysis of how one can estimate how a piece of wire with a current flowing through it radiates in space. And by making a collection of wires and calling that an antenna, these models break down the wire into small little segments and adds up the little radiated fields from all of them in order to create an antenna pattern. And so what's shown here in the picture is literally from Saturday, where here is a handheld analyzer with a piece of coax that has a connector right here that has 4 red wires. You can see the 4th one in the back there hiding behind it, off of the ground. And then the center pin is literally attached to a white piece of wire, which was made shorter than its original length simply by bending it backwards on itself. And this being 70 centimeters, which is where the club has one of its repeaters, 70 centimeters being 440 something megahertz in this case, the antenna is physically small. You can compare it to the size of a hand there, shown in the same picture, which made it fun to play with. Same techniques here can be applied to your A and N-fed HF antennas or anything else. But today, we're really going to focus on the basics and just get your hands wet trying to model this thing. When we were in the class, we started with the wires straight out, like a regular ground plane. And we started with this white wire full length before starting to bend it back. And then we started to bend down the red wires, and we could watch on the meter how the 70 centimeter band, which goes from the left edge here to the right edge here, has this funny little sloping white line that kind of dips down and comes up. That's actually an SWR curve. And so we were tuning the antenna by altering its physical shape. So far, so good. Any questions? I'm looking for hands raised. Don't see anything. But that's it. In simple terms, an antenna is a collection of wires. They could be rods or tubes or solid surfaces made out of metal or towers or anything else that radiates. In this case, it was fairly thin wires. You wonder what happens. What if the wires were thicker? What if they're covered in plastic like these were? That all has an effect. And so these wires have properties. They have diameters and material properties. Some of them are made of aluminum, some are copper, some coated, some not. And from a modeling perspective, wires have endpoints. So this is a 3D antenna. It's in 3 dimensions. So we use an X and a Y and a Z to represent the points of a wire. For example, let's look at the wire here in the bottom picture that calls itself number 1. Well, number 1 goes from down here in the up direction, which is the Z, for some length like that. There's also an x-axis, which is generally sideways one way, and y, which is generally sideways the other. And so any point in space, like the center here, which we arbitrarily said is at 0, 0, 0, and any other point, like the end of the white wire up here, which would be 0, 0, and a z coordinate of whatever that z value was in terms of its length. Have I lost anybody yet? Okay, some heads shaking. No, haven't lost anybody yet. No hands up. I'm not hearing any voices coming off of mute. Oh, there's one. Mary, go ahead. Mary and Lou.
I was just raising my thumb saying I'm good.
Oh, okay.
That's a
It's a
reaction.
small font here. My apologies. I got my reading glasses on, but to me it looked like a little hand. I got it. Thumbs up. Thank
So
you.
do I. I've got my reading glasses on.
Yeah, oh, by the way, I'm Jim.
good.
I don't know if I introduced myself to everybody, Jim. Yeah, I think John did. Thank you. All right, so that's the introduction. So when we were going into this build with the little tiny antenna that Chris came up with, he had pre-cut the lengths of wires with the one that was on the top here. I think he had it around 7.5 inches, and the ones that were down for the angles, he had pre-cut them to like 8 inches. But with any computer model, you want to know, does it pass the Snicker test? Is it reasonable what's being asked for? And so there's websites that can help you with any kind of antenna that you're looking for to see if what you're getting back from the model actually is sane compared to reality. And so here's one at m0ukd.com. So a ham over in England offers a calculator for a quarter wave ground plane antenna on his website. And you can do measurements in your favorite units: millimeters, centimeters, meters, inches, feet. It's all the same antenna. It's just going to be measured a different way. So here live, and I'm assuming this is coming through on the screen. Okay, here, yeah, I see some nodding. Yep. You can basically type in whatever frequency you want. So let's say we said 435 megahertz, which is right in the middle of the band. There's a thing called velocity factor. That's pretty advanced. We can get into that. And then you pick your unit, inches or something, and punch the calculate my quarter wave, and you come up with a value for the A and for the length of the B that you would replicate for all of those. And you can see in this case, they're suggesting that it's 45 degrees below straight up for that bend. So that's another variable, obviously, that we can play around with and do some what ifs. And so I'm just going to roughly, here's the two numbers you can kind of keep in your head. Somewhere around 6.5 inches tall and somewhere around 7.25 inches long might be what you'd expect or want to be working with. So Chris gave us wires that were a little long on purpose. The material that he gave us was a thinner wire. These could be tubes, but you get the idea. Any general questions about the concept? No. So let's go ahead and adapt it into the next thing. First, realize that a model is just an abstraction. And you're always trading off how long it takes to crunch the numbers with the precision that you're looking for, with meaning like the accuracy of the numbers. There will still often be the need to do a little tweaking, but my gosh, these programs are so full that if you wanted to, you can minutely set all kinds of variables. I don't. I usually just try and get in the ballpark. And what I mean by getting in the ballpark, well, this thing, and here's that wires diagram of it before, with the wires numbered 1, 2, 3, 4, 5. This antenna will have 5 pieces of wires that we're going to model. Good enough? So we have the letter A, which is the one vertical wire, which we now know should probably be around 6.5 inches to make it good. And the B, which we will have 4 of those, we'll call them the leg wires, about maybe 7.25 inches for those. And we have connection points. Let's call the middle this 0, 0, 0. And then the wire A goes straight up to a 0, 0A. So far, so good. We have a feed point. Obviously, there's our connector or something like that. Over in the model, you'll find a funny little red circle. That's going to be the software's way of showing you where the feed point is. It actually puts it in the center of the smallest segment. I don't know if you remember me mentioning segments, but the model breaks up a wire into a whole bunch of virtual segments so that it can add together the little radiations from currents flowing in every single one of them. So, all right, let's say we made this, was it 6.5 inches? What if we said make it have 51 segments in your model for that 6.5 inches? Well, it'll model the feed point against abstraction in that first segment, the way that we're telling it. That was a lot to absorb. Have I lost anybody yet? One of the things that I will bring your attention to, if you have extra time, is in that zip file, which you may have downloaded, there is a PDF file called Radio Software Series for NEC. And if you open it, which I will try and do here, of course, it opened on a different page. Let me bring it over. One moment. Here we go. You'll see a number of slides in here talking about the general capabilities and how you might model and work with HF antennas and things like this. And if you really love dipoles, you know, the simple dipole, and you started wondering, oh, what if you bend the ends backwards? You can get here's your horizontal dipole. Well, what if it looked like this? Or what if it was vertical? Or what if you folded the ends back? Or what if you started bending the ends up or sideways or this or that? These are all the kinds of what ifs that you can do. And it kind of steps you through how to do the modeling with it and maybe some of the things to expect. What I was trying to get to was this. When you did your 4NEC2 installation, there are a number of folders that get created, including one called models. And inside that models folder where you installed the 4NEC are going to be all kinds of examples. Let's take a look. In the 4NEC folder, I'm going to bring this onto the screen. We're gonna be doing this in a minute. So if you don't remember where you installed it, you can always just look at the properties on this right here, and it will show you. In my case, I installed it in amateur radio GCARC. Little trick. Here is that folder, and here is the models. So if I go into models, you'll suddenly start seeing, and I added the field day and a GCARC demo. But look at this, aperiodics, fractals, HF beams, collinears, on and on and on. And each one of these folders, whatever they are, like HF simple, will be full of different models here for you to explore at your heart's content. I find it's always easier to start with somebody else's model and then tweak it for what I'm trying to do. At least until you get used to this. Some of the models are pretty straightforward. A Moxon. Here's somebody on their roof. Here's that little red circle. Put a bent dipole on their roof and then put some other wires out there for a director and a reflector. Here they've modeled some complicated antenna here. Here they modeled an entire battleship. Here is a multi-dipole thing with a ground plane in the back. Anyway, have fun. There's a lot you can go through. But this is the segments part I was just talking about. Whatever your wire is, your dipole or anything else like that, in this case, 11 segments, you get the idea. Come back to that anytime you want for a reference. I only have one slide left before we do the demo, so let me jump to it right now.
Jim?
Yes, go ahead.
Where was the reference to finding where those models, what folder those models are in?
So it's going to be in the folder where you installed your 4NEC. And so one of the things you can do is a trick, because I always forget where it was.
Yeah, me too.
Was hit the Windows key, type 4NEC2, and then have it open that folder. And when you have it open that folder, you'll get something that looks like this. And then you can right-click on this to look at the properties of where that link is pointing to find out where you installed it.
It's taken me to the setup.
Okay.
Don't wait for me.
Okay.
Don, when I installed it, I just did all the defaults and it installed it right on the C drive. So maybe check there.
Straight into C?
Yeah, just put it right on C. So
Oh, yeah. Okay, I got it.
yeah,
Thanks, Mary, never mind.
I created a folder called 4NEC2 and it installed it on there, so I wouldn't have to remember where it's.
Nice. The files that we're going to be, so I'm going to go back to this one. In the forum zip or in the email, you'll find a couple of special NEC files that are named for today's class, so you don't have to build them from scratch. I'm kind of recommending this one. One of them's called the ground legs at an angle down, and the other one was the legs straight out. Those are the two that we're going to play with together. So if you can find where you put those, that's where we're going to be going next. They wouldn't have been in the standard installation. They were just for today's class. All right. I wanted to point out this because I'm going to show it to you in the live software. The tools help you build and manipulate the model that you want without having to, do it physically. So you can create any kind of symbols or equations that you want. These are simple equals, but you can do fancier things here, which I'll be demonstrating shortly. But in the case of our model, there's a thing called velocity factor. Okay, it's time for me to come back to that. If you're in free space and you're working at the speed of light, the velocity factor is a 1. But anytime you're working with real wire, copper, aluminum, whatever, it's less than the speed of light. How much less? 3%, some percent, depends on the material and stuff. And it depends also on whether or not you have a coating on the wire. Now, these models let you go crazy with the coatings. You can say whether it's PVC or this or that and all that. All that fidelity is in the model. But again, a model is just an abstraction. And so I find it a lot easier to simply use a velocity factor for insulated wire, which is what we have here when there's plastic on it of some sort, of around 0.95. And this will get me in the ballpark to start with. So that's what I'm going to do. The length of A, 6.5 inches. The B, 7.5, 7.25, and I'm using inches. I'll show you where that gets picked instead of picking centimeters. And then a thing called an angle. I didn't want to lose you this on later, so I just wanted to point out the angle right now. I chose in my definition to say the angle was relative to being straight up. And so in this case, for a leg that is bent down or for a leg that is straight out, the leg that is straight out would be 90 degrees. And if I want to bend it down further, I have to go beyond 90 degrees. In this case, if I went another 40 to make that 45 degrees below the first 90 degrees, I'd be at 135. And so that's what's being modeled here. Lost anybody? So here comes the first quiz. I got 2 files here, one called angle down and one straight out. The example that I've been showing here with 90 plus 45 equals 135 is probably in which of these 2 files?
Would be the angle down one, right?
Yep. Yeah. So that'll be one of the differences that you'll see between these 2 files is, and you can literally go into yours and start changing this angle 135. You can type any other value that you want. Okay, now it is time to open a model in 4NEC, and that's what we're going to play with together going forward. So go ahead and start your 4NEC2 program, which you can do by hitting the Windows key in 4NEC2 or finding it on your desktop and launching it. And I will show you it running, but this is the important set of graphics. And you don't have to memorize this. We're going to go together. We're going to start on the left with this one that allows you to open an NEC file. And we're going to work our way towards this thing that looks like the calculator, which allows us to go ahead and calculate all kinds of things associated with the frequency in use. I'll show you the other fun ones as we go. This edit an NEC file right here, we'll use that one. Probably skip the Smith charts, just wanted you to know it was here. 3D, we'll take a peek at that one. And lastly, I'm going to mention this thing called an optimizer. Yeah, enough said on that until we actually get there. Okay, it's time to start your 4NEC program. And when you do, several different windows will appear. There'll be one like this. Don't worry about its contents just yet. There will be one like this that kind of shows a picture It may not yet have the wire numbers tagged, so it may just show you whatever kind of antenna it decided to start with as a default. We have not loaded yet the one that's of interest. And down here, you may or may not see some form of a pattern. Right here are those pictures that I was talking about, and I can put up again, perhaps in the background. One moment, right here. And let's see if I can put the 4NEC in front of that. Yeah, I'll minimize that. So this is this. Everyone's sort of with me so far still? Maybe. It looks like my meeting participants, I've lost them. So I'm going to click this button so they show up again. Hello. Yep, there you are. Any hands up? No, we're good. All right. So inside of here, we're going to go to open up a file that is of interest. And when you do, an open file box will show up. And I want you to go to wherever it is that these two files are that you've put. In my case, when I unzipped the file into this folder, that's where they appeared. And I'm hoping that you will click on the legs straight out and put it here. I'm going to wait for a moment as people work on that. I can see some people's videos here. Some people don't have the videos. Anybody wish to have a few more seconds to find that file that has the legs straight out? Not hearing any complaints yet. That's a good sign. Okay, let's assume you're there or can catch up. So in the open files, we do that one and go ahead and open it. If you're lucky, you'll see a geometry show up that has a model that looks like this in it. And again, it probably won't show the wire numbers, so it might look something like that. Close enough? For those people on video, I'm looking at facial expressions. I got some thumbs ups. Yay, all right. Okay, there it is. Now, you might not have any data in here, but let's go to that calculator. Okay. And when we push the calculator, a new thing will pop up that looks something like this. And hopefully it looks a lot like this. What we'll see in here is a frequency that's pre-populated and an option to push one of these radio buttons like far field pattern, frequency sweep, near field pattern, full vertical, horizontal, resolutions of 5 degrees, all this kind of stuff. I'd like for us to pick the far field pattern. And really, that should have been the only thing that we needed to do here, and then go ahead and push generate. When you push generate, another pop-up's going to happen, and there'll be a little green progress bar that will happen, and then there'll be like a ding noise on your laptop if things go well. And potentially something like this for pattern will appear. So far, so good? All right. So in the pattern, we can show indicators, info, the structure of our antenna right there. Okay. We can show info, which may be hard on the screen, but here in green, in both of these lobes, from there to there is the beam width. That's the 3 dB point. And here are the direction or directions in this case of the greatest gain, which looks like it's about 2 dB in this direction. I'm going to jump ahead and ask you to push the 3D button. When you do, another picture of our antenna appears. Now, the interesting thing about this one is it defaults to hide the pattern. Now, we just ran something, and so I'm going to click on transparent. And then up here, I have a thing called zoom, and I'm just going to go click to the left twice. And now what I'm going to do is I'm going to hold the left mouse button while on this picture and drag it slightly in order to change the view. And what we see here is that donut kind of a thing that everyone talks about around a wire in space with a ground plane in this case, creating a donut. For fun, we can come over here and do multicolor. Okay? And all of a sudden, a dBi scale shows up here, color-coded. And now we can spin this thing around and look at it from the top and the bottom and all this. And in free space, there's no ground in this model. It's just like we would expect. The bulk of the radiation is off the side of our piece of wire that goes straight up in the air. And when we look down on that wire, it's like a blue gap in the donut. It's not completely filled in. It's -3, -4 dBi or something, but clearly the energy's been squeezed out the side. I love this tool. All right, I'm going to go ahead and close the 3D viewer, and I'm going to go back to running. Here we go on the screen. And this time I'm going to go to the next button down called frequency sweep. And when I do that, we're also going to have to put in the frequency range. So what this is going to do is help us so that I don't have to pick every single frequency in the band one at a time in order to draw a curve. We're going to let the software try them all and draw the SWR curve for us, just like if you were reading it on a nano VNA. Okay, so we go back to do a generate, just like we did before for the far field pattern. This time we're going to click on frequency sweep. And I want us to fill in the 70 centimeter band. So we'll start at 420. We will go to 450. And then we'll pick some sort of a step size for it to jump, going from 420 to 450. You can pick whatever value you want here. I picked 0.25. The smaller the value, the more time it takes to run, but the more precise the results will be. This will take a few seconds, depending on how great your laptop is. Mine's a few years old, so it definitely takes a few seconds. Ready to generate? Here we go. And what happens? We get a little DOS window saying it's doing this. We get a little progress bar going here in the green. Click, 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 click. And then finally, it gets to the end and another ding. And this time, another window popped up. Anybody else successful with a frequency sweep and ending up with a window like this one called gain SWR impedance that pops up? Excellent. A thumbs up. Questions, anybody? What we're going to focus on is not the reflection coefficient. Just kind of ignore the bottom side here. And we will simply look at this top part here that says 50 ohm SWR. Effectively, what we're doing in the computer right now is as if we had our vector network analyzer that was shown in that early picture with someone holding it in their hand attached to an antenna, which in this case, the antenna is in the computer, and it's showing us from 420 up to 450 a predicted value of the standing wave ratio. What we can see here is an SWR of around 6 at the low end, a lowest SWR somewhere just over 2 near 444 megahertz. And then it starts to go back up maybe around 2.5, somewhere in there by the time we get to the top of the band. So the key here is there's an SWR curve. It is skewed towards minimum point right now towards the higher end of this band. And even at its lowest point, it's above the 2-to-1 SWR. So let's peek at our antenna again here. We have a vertical element. We got horizontal radials straight out, and we have a curve like this. I wonder what the impedance match really is at our frequency of interest, which halfway through was 435. According to this, the SWR is probably somewhere around 3 there. Should we make a better matching network? Can we do other things? Let's go back to calculate real quick just to do this one. Far field pattern, generate, boom. And we're back to what we had before. But now I want us to focus on the data that's inside of here. I'll pause for just a moment to make sure that we all got back to what we did before, which was to execute far field pattern once. But now we're going to look at this stuff. Look at the complex impedance here. Look at the SWR, which we saw from the curve is probably near 3. It is 2.86 at our frequency of interest. So here you can get things at a glance, or you can look at the curves, whatever works out best for you. How might we lower the SWR for an antenna like this for the frequency of interest when we saw what the curve looked like before? I'll open it up to suggestions from the group here. What are some of the things we might physically do to our antenna if we had a vector network analyzer attached, or in the model that we could do virtually to try and get a lower SWR at the frequency of interest? You can come off mute and just shout out. Mark, anybody? Rob?
Change the length.
Go ahead.
Change the length of the Z.
Yep. Change the length of the Z. Can shorten and shorten it or lengthen it. Yep. Sounds good. Anything else?
You could change where the feed point is, like move it over.
Yeah, I could move the feed point. Up, down, or wherever. Yep.
Or you can create a matching network if your heart's
You can create
set
a
on.
matching network. In fact, the software here, I'm glad you brought that up, tells you that if you wanted to create a matching network, it's actually telling you how many microhenries in series or parallel in form in order to help you build such a matching network if you wanted to. Yep, that's pretty advanced. Anybody else?
We could bend down your XY.
You could bend. Did you say was that Doug talking?
Yeah, bend down the XY. I know we're doing
Right, bend down the XY. If you remember that picture that we were showing of what was built, it kind of looked like somebody had bent those things down. Okay, it's time to play. Let's try something. On this main menu is this, I don't even know what that thing is. It just says, when you hover over it, it says edit NEC2 file. And when you click it, it comes up with all of these tabs. I want us to go all the way to the symbol one on the left. When you do, so again, I went to this funny little thing here. I don't know what it is, a book symbol or something. Edit the file. This is what comes up for me, and this looks just like what was in our slide when we were starting the presentation, along with the row 6 and row 7 that I had hidden before. One of the suggestions was, let's change the height. Okay. I'm open to suggestions. We're at the 6.5 now. Let's change it by a half of it. So, by the way, the units is the scaling is down here. Like I said, you could change it to be what you wanted to use. In this case, we're using inches, and it has so it internally it'll convert it, but we can read these things in inches. Who wants to go up to 7 inches, or who wants to go down to 6 inches? I'm open to suggestions. You can play with your own value. Shout out. We'll see. We'll see who wins. Or type it into the chat window. I'll watch a few. Well, I'm going to go up to 7. Okay. I'm going to do that because when Chris handed out the pieces of wire, they were a little long to start with. We kind of know the answer should be somewhere around 6.5. But what if we just started with 7 without bending anything back, without shortening it or doing anything else like that? Done. Over here is that exact same. You could either go up here to calculate, or you can just do it to calculate here. When I'm making quick changes like this, I go over here and push the same one. It comes up with this one with a little box saying screen data used. Well, what does that mean? That means I made a local change and I'm not using what's in the file. Now, up here you can see file changed, but I didn't save it. Okay, so screen data, far field, no. I'm going to sweep. I'm going to sweep using that changed value and same range. I'm not changing the range or anything like that. Here we go, generating again, watching our little green bar until it comes up with the answer. Hearing the ding, and then it draws me a picture. Oh my goodness, this is a different looking SWR curve now, isn't it? I went from 6.5 inches up to 7 inches just for that letter A, the thing that was sticking straight up in the air. What happened? I thought the low point was around 444 megahertz. Where is it now? Lengthening the antenna did what to the resonant point of this antenna?
Lowered.
I saw John saying lowered. I didn't hear him. I think he was on mute. But yeah, somebody else said lowered. Right. The curve used to be over here like this with the dip around 440, and now it's down here. We're now getting a better appreciation of playing with antennas just on our computer. I didn't need a vector network analyzer. I didn't need wires. I didn't need to be stringing things in the trees if I'm an HF or something like this. I got an appreciation that I can, as was suggested, I can change the length of the vertical element here, change the height of this Z, and influence where the low point is in the range of frequencies that I'm looking at. And by making it longer, I bring that resonant point down. So conversely, if I want to move this back up, I would shorten it. Go ahead and try it in your model. See if you remember the steps. Click the funny book. The height, 6.5. Make it anything that you want. 6.75 in my example here, if you're just following along. Punch the little symbol here that brings up the screen data used, and go ahead and run another sweep. Now I'm tired of waiting, so I'm going to change my 0.25 to a step of 0.5, which should make it go a little bit faster. And it's not, you can see there's fewer dots on the screen, but my gosh, I can tell what's going on, right? I don't need as many points filled in. Sure enough, I moved a low point that was down at the bottom of the band up into the band, though I used 6.75, and so here, down here, it was when it was 7. Here is a 1/4 inch taken off that antenna. If I take another 1/4 inch off, I'd have it back up here. Everyone good with the concept of changing the length of A? I'll listen if anyone wants to come off mute. Now we still have another problem here. I'm still above 2-to-1 SWR. I heard changing the feed point location was a possible suggestion. I heard bending the radials down was another suggestion. I'm going to show you this, but I won't spend time on it. You can play with it. Back in the book, where we've been looking at the symbols here, there are other tabs. One of them is called geometry. I'm going to click that. Lo and behold, here are 5 things in the geometry, which are called wires. And we gave them numbers, 1, 2, 3, 4, 5. Okay. Over here on this picture, go ahead and click the show and wire numbers. Lo and behold, here's wire 1, 2, 3, 4, 5. There's wire 1, 2, 3, 4, 5. So wire 1 is clearly the one that goes straight up in the air. Let's see if we can figure that out from the points in space. Look at this. Here's an X, Y, and Z one, and here's an X, Y, Z number 2. So what did we say? We start at 0, 0, 0. Well, there's 0, 0, 0, and we went straight up, which is the Z-axis. 0, 0, and how far up did we go? A, right? 0, 0, 0, and we went up to 0, 0, A in height. So far, so good? So this is a very simple geometry. Obviously, you can get more complicated. I'll pause for a moment. There's more fields here. There's a field called radius in comments. So radius allows you to do things like, how fat is this wire? I put in number 20 for 20 gauge. I think we actually use 22 gauge, which is thinner in the class. Here's 22 gauge. I could put in 0.0254 wire diameter in inches. I'd actually have to convert it to metric though, because this page doesn't have the metric. So 20 is as thin of a wire as the model uses. But you know, for fun, I could make that a piece of 12 gauge wire or something like that. And when I go ahead and do my model, I'll punch it again, and I can do a generate just like before. Get the hourglass here. It's working on it, working on it, working on it. Right? Not all wires have to be the same thickness. I've made this thicker, and you can see the effect on the SWR curve compared to where it was before. All right, all the kinds of fun things that you can do, but we're still stuck with this up here. So unless I change the feed point, next one, where is the feed point? Well, it is on wire number 1. It is on tag number 1. So I'll go back to the geometry. Wire number 1 was our vertical one that goes up to A. So I could put this anywhere I want on there. How many segments? Well, I said there were 41 segments. Always try and use an odd number, okay? I said there's 41 segments on there. So literally I could put that source on any segment that I wanted to on the vertical here. I just put it on the very first one, which was closest, which was at the beginning of the wire, it was at 0, 0, 0, at 0, 0, 0. So that's why the little red dot appears here, but you can move the little red dot to wherever you want. And that's one of the things that you can do when doing a dipole. You just make a long piece of wire and literally put it either in the center, the middle segment, or if it's an offset dipole, put it in any other one. So far, so good. But in this case, we're not going to do any of these things. So what I want to do is close this. File is changed. Do you want to save changes? No. Let's just keep the original the way it was. We're going to go back to open files. And guess what? It is time to now play with the one that is called legs angled down. Anybody want me to pause for a moment? Going back to the file open, wherever it should default to wherever you last looked. I'm going to go ahead and open the legs angled down file. Okay. So again, you probably have some things that are showing up that In this case, the legs are not straight out. They're angled down. So what does that funny little book thing look like in this case? Let's bring it up on the screen and take a peek. What does it look like? The geometry is the same as it was before. All right, here's our first wire 0, 0, 0 from 0, 0A, and none of the other values changed at all. We literally did not change the geometry. We must have changed one of these symbols that was in use. And lo and behold, we did. It's on the row 5 here. So back on symbols, here it changed from 90 to 130. Don't believe me? You just put the 90 back there, hit enter, run something, and it'll go back the way it was. Think like this. Okay. But in my case right now, I want to do the 135 the way that this file was. Okay. So you can try any other angle that you wanted just to see what was more optimal. And let us do, I'm going to put it on the screen again. Let us do the frequency sweep. Same range as before. And see what happens. Bring it up on the screen here. My little green is moving across. In a moment, I'll get a ding. And what? Take a look at this. What happened to the SWR curve that we'd been looking at before? If you're talking, John, you're on mute. Anybody else want to come off mute? What are some of the things that you're seeing? How does this compare right out of the box to what we were looking at before? Remember, originally we had 6.5. It's still at 6.5. 7.25. Still 7.25. What is different right now? What are we seeing that? It looks like I lost.
You have a better impedance match.
Okay, yes, I guess I accidentally closed it. I'm going to rerun it again. Somebody said you had a better impedance match. Can you define what it is that you mean by that?
Well, you're closer to 50 ohms now, where you
Look at
weren't
that.
before. So you're
Yes, my low point is not above 2. My low point is now close to 1-to-1. Good. Anything else that you observe? We're looking at the top here.
You have wider bandwidth.
You have a wider bandwidth. Look at this. Yes, the same frequency range, 420 to 450. The range of frequencies that are, below 2-to-1 SWR or below 3-to-1 SWR. Oh my gosh, the entire band is below 3-to-1 SWR. Just by bending those things down. Huh. Anything else that you see? I gave you a clue. Where is the resonant point compared to the very first time that we ran the thing with the legs out?
well, you're in like the 120 in the 427 range where you were 444, I guess the first time you ran it.
Yes. Yeah, the first time we ran it, the curve started up here around 6, came down near 2 around 444, and then went up. So the lowest point was over here. So bending the thing down moved the spot where the lowest is from here down to here, and it lowered the entire curve from being up here to down here, a better match for our 50 ohms. So we've already learned before that if we made the wire longer, that we moved the resonant point down. So in fact, bending those legs down had an effect of shifting this point down in frequency as if we were lengthening the antenna. but it also gave us a much flatter curve, as was pointed out, which gives us a better SWR bandwidth. And by lowering the whole curve, not just making it flatter, it gives us a much better match at certain frequencies. Okay, so my operating frequency of interest is 435. It's not here. What do I do to my antenna now in order to get this dip closer to 435? What do I do to it? Here's my antenna.
You shorten it.
We got one vote for shorten it. Any other suggestions? Anyone? Doug?
For lengthen Z.
What would I be lengthening, do you think?
Z.
Lengthening the Z,
Vertical.
okay. So the last time that we lengthened the Z, it moved the low point from here. I think we got it to move all the way down. So I think in this case, if we lengthened the Z, we'd be pushing it off to the left again. So I'm kind of inclined to go with the answer of shortening it. But let's see. I mean, that's what this is all about. You know, let's experiment. Let's try. So if you can click your 3D part again, and assuming it's still on the screen here to find your this. Here's the 6.5. What do you want to change it to? You can randomly pick values, and I guess I will. Let me take a 1/4 inch off. I'm going to chop a 1/4 inch off. And
I
I'm
want
going
to change it to 6.3545.
Hold that thought. That might be a good idea. Hang on a second. I'm going to do a frequency sweep just to confirm that by shortening the vertical, it should move that dip point higher in the curve. Did it? A little bit. Now I want to show you something that's more advanced, okay? I just want you to know that it's in here. You see this thing over here that when you hover over it says start the optimizer. Well, it says please close the edit window first. So this funny thing here, not the one-to-one, but the thing next to it. And effectively what they're saying is close this. And why? I'm going to tell it, okay, computer, you go change the value of A however you want in order to try and give me the best SWR match at the frequency of interest. Do I want to change it? Nah. Here we go. Starting the optimizer. Does this come up on your screen? I mean, you can do a whole bunch of hand edits. Just think of like if you were like we were on Saturday, we were bending the top of this antenna down a little bit at a time to try and find the right thing. We bend it twice and measure, and then we try and do some math and all this. My goal here is what do I want to optimize? The gain, the front back ratio, if I had a beam antenna or something like this? No, I want 100% optimize the SWR. Okay. How am I going to do that? Well, I created symbols when I built this thing, and one of the symbols was the letter A for the height. So I literally just click on A and look what got selected. Can you select more than one thing? Of course, but then it takes an exorbitant amount of time to run. You'll see if you wanted to try that. So I clicked on A to put this in here, and now I'm going to click Start. And I'm going to watch what happens to the model. I should actually see the height changing a little bit as it tries in this variable values. It's going to try a whole bunch of different runs for different values of A until it comes up with what it thinks is the best solution or a good enough solution to this answer. What was your guess of what the value should be? You said 6 point what?
6.3545.
I don't know if you ran the optimizer. I'm ready to push the optimizer. Everybody else about ready to do the same, or go ahead and do it on yours. Let's see what happens. Oh, it's starting to optimize. And look at the height's going up, the height's going down in the picture. It's moving around. It's trying all these different values. Oh, it's homing in somewhere around 6.35. What a coincidence. Oh, look at that.
Oh
It
wait,
ran.
you got a different number. You want one more.
Oh, okay. So it took me 16 seconds to what probably would have taken anybody else an hour to do by hand. So you get the idea? 6.35 is what it thinks is a magic number. So I'm going to do that. I'm going to now close the optimizer and go back to this this edit thing here. And I'm going back to my symbols. And I know the answer that I want to put in there and see if that helps. 6.35. I'm not changing anything else. And I'm going to go ahead and I'm going to run it. And here it is. I want to sweep the range using those screen data. And it's trying. Oh my gosh. Is this a miracle or what?
I got the same curve at 6.3.
Nice. Now I'm slightly above
Actually,
1-to-1, so I could
my
actually
curve-
change my bend angle. I could play with any other kind of thing right now to see if I could even do better, but why bother? I'm below 2-to-1 for the whole band right now. Gary, you were saying something? Go ahead.
Yeah, I got the same curve. And everything is below 2, and it's even lower when I put in 6.3.
Nice. Okay, so
think
this
it-
is just an approximation. Realize that I have a velocity factor here of 0.95. Your particular wires might act a little bit different. The easiest thing to do is get you in the right ballpark and use your equipment to help calibrate your models. If you like using the same wire over and over again, find out what the right values are by doing a couple experiments. It's like, ooh, it actually physically resonated at this frequency. The model said this frequency. What do I have to change in the model to do that? Oh, I'll change the velocity factor to be 0.94 instead of 0.95 if I really wanted it to be more accurate. But quite frankly, if you're building 80 meter or 160 meter antennas, you can be off by feet. We're not talking about quarter inches here. And it isn't even going to make a difference. So it all depends on what you're doing. If you're doing 70 centimeters, a couple of tenths of inches makes a big difference. What do you think? Here's been the quick introduction to using a piece of free software like 4NEC2 to try and do some what ifs associated with an antenna that you've either already built or were thinking of building or saw other people building or whatever. Now you can play to your heart's content. What if I ran the optimizer, changing the angle? On and on and on.
Jim, you this is in free space, right? Not over ground.
Correct. Okay. Is there a question in there beyond that? Yes, what is modeled right now is in free space, not over ground. Do you want to put it over ground?
If it's not too much trouble to do that, it would be interesting.
Okay. I'm going to do it live. Hope you don't mind. When you put a ground in here, it will assume the ground is going in at 0. And unfortunately, while this antenna is being built with a reference point of 0, 0, 0 in free space, this part of the antenna would be inside of the ground, so it won't like that. So effectively, in my geometry, I end up having to adjust all of the Z points to represent how far above the ground that I'm going to put in do I want my antenna to be. So the easiest way to do that is create a new a new symbol, which is called I don't know, make something up, height. And this is all in inches. So I don't know, 120 inches? This is a rather advanced question. Maybe I shouldn't have taken this one first, but I'll just do it anyway. So I'm just gonna go ahead and add the height to every one of these. Make sense?
Oh, okay. Well, that's easier.
Okay. Or I can make a new symbol and use that. Oops, I didn't do that one right. Do it again. 0 plus height. 0.
Why can't you
plus.
just say height? Why do you
Oh.
need 0 plus?
Oh, you know what? You're right. In this case, that's height.
No, I just wanted this as a syntactical thing.
You're right. No, just what I was thinking ahead to was the next set of z values. Okay. Over here, I have a plus height. Make sense? And bz plus height. We'll see it in the picture in just a moment. Plus height. Plus.
Seems like they should have a simpler way to just say move the antenna up to this
Yeah.
height.
Well, most
instead.
people aren't building antennas in free space. They're thinking ahead. They're going to model it that way anyway. But that's what I did. So I changed the geometry. I'm going to click this thing and I'm going to do a far field pattern.
How
Not
did
a
you add
frequency
the
switch.
how did you add the column?
He didn't add a column, he added a row.
Oh, so I'm going to go back to some.
Because you have, I only
let me
have
cancel this. So
I only have 2 columns. I can add a row, but
so over here on symbols, I just invented a new symbol and I called it height, and I set it to some number of inches above ground.
okay, but I only have 2
Okay.
Yeah, neither did he.
So let me say it was 12 inches above ground. Okay. Then for the geometry,
the geometry.
I went. All I did was all the z's used to be 0 here, and I now set them to be height. And over here, they just were a and whatever they were before. I just added a height to those as well. And hopefully, if I did this right, when I calculate the far field pattern, something in the picture here just happened. And what was it? Oh yeah, look at that. My antenna jumped from being down here centered on 0, 0, 0 to up here, and it calculated some stuff. It's easier to see in 3D. So I'm going to try and click that 3D button again, and I'll bring that one over. And look what I've got. There's my antenna sitting 12 inches. Everything's 12 inches pushed up into the air. And now when I do my multicolored pattern, and you can change it like this, you can see that I'm now 2 dBi, so it got a little stronger. Where you can really notice this is with dipoles and other antennas that are horizontally polarized, because they have a good ground effect. I'll show that if we have time.
So wait, Jim, why is the pattern below that?
Oh, I think it's just a strange way that the model always still references everything as if it was in the center. Oh, you know what it is? I moved it up, but I forgot to do something very important. Oops. Symbols, geometry, source load, frequency, ground. It still says free space. I'm like, where's the ground?
Oh, okay.
I forgot to put the ground in. It's still in free space. Thank you. So you can model any kinds of grounds, perfect grounds, real grounds, make your own, and you can decide, oh, it's an average, or it's good, or it's dry, sandy, coastal, or it's in the hills, or mountainous, or whatever you want. I'll do that now. Let's put it back in the picture. I'll run it real quick. There we go. There it is. There's the ground.
Yeah, obviously with a ground plane antenna, the ground doesn't have nearly the effect that a horizontal.
But notice how my nice loop that I had before that was rating it out like a donut. Here's the ground, because this is the side view, And so the info on this one is showing, oh, I have a takeoff right here at about 25, what is it, 25 degrees is that's where my biggest lobe is. And thank you for pointing out the fact that I've got ground there. So now I have a low radiation angle here, and you can adjust the height and see how that affects. But yeah, it'll be more pronounced if you're doing a dipole over ground.
So before you, when you had it set to free space, the radials were below the ground, but they weren't below the ground because you said it was free space.
Yes.
Okay, I mean, what would it happen if you didn't do the offset and then said it was ground? So the radials literally would be below the ground.
Yeah. So it'll give an error. I'm going to do that by saying the height is 0. I'm going to put it right back the way it was now that I have all the symbols in there. And when I say generate, I got an error. I got an error.
Okay. Pretty cool.
It does, and here's the picture, kind of reinforcing the fact that no, that is not a good model.
So that radiation pattern though showing stuck to the ground. I thought the radiation pattern with the quarter point with this antenna would be attached to it. Wouldn't that donut like be up there with the wire elements or no?
In reality, yes.
Okay. Okay. No.
It's just the way that
It's
the
viewing.
model graphics works. It always shows it down here, no matter where you had it.
Fair
I'm
enough.
sorry.
No. Fair. I just wanted to make sure I understood that right, and then
Okay.
otherwise would be like, oh no.
All right. All right. Great question from Al about what if I did this over real ground? Yep, it can handle that too. And what if it was sand? What if it was this or that? Well, you can see again, if you want to play around with what your ground is here, you can change your ground conductivity and all this, or pick from one of the dry sandy coastals or whatever you wanted. Next question.
What's the source load tab do?
I think you're gonna, we took a quick look at it, where this tells you where to place that little red circle. And, some antennas literally will have more than one feed, right? If you had a collinear arrays and phased arrays and stuff, you can have more than one feed point. Sometimes I can have phased verticals, so I can shift the phase between my two verticals and see the radiation pattern that would come out of that. You can go crazy.
And so that would be if you wanted to feed it at the base point of the vertical element, and let's say and the top of the vertical element, you would do that by saying
you could add another
segment or something.
Yeah, you'd literally add another source and say what tag number, meaning which wire to attach it to. I'll attach it to the first wire, but this time I'm going to attach it out at number 39 or something like that.
This is where you need to look at the other examples.
Yeah, follow another example. And since I'm off the top of this thing, you have to trust me. Here, I just put another red circle up here. So I'm feeding both ends at the same time and in phase, according to this.
What that looks like.
Try it on your model.
Well, I don't want to mess my model.
Well, I'm going to do this. As long as the screen data is used, I'm not messing anything up. It didn't like it. Something's wrong. I don't know what was wrong.
Well, wait a minute. It didn't like it.
It did something wrong. We're off script.
Well, but what I'm wondering about is that's not in the case of having your radials below ground is an error. Theoretically, you could try and feed this sucker from the top and the bottom, and it'd be interesting to see what happened.
That is true. It said to run the error check, which I don't want to tie everyone up for, but there are, wherever it is, I don't know, the error checks in here. It can help you figure out what's wrong. What I'm gonna do in my last, I'm not going to save the changes. There are all kinds of other models that were out there, including those bent dipoles that you can see, or this or that. Last field day, I created an antenna. Well, I thought that was the antenna. Yeah, it looks like let's see. Thanks for presenting. Hopefully recording will be accessible. You're welcome, Court. Let me run it again. Any other anybody else playing around with something and have a general question that they want to ask? I just wanted to show an example of running one of the simple antennas. So I'm going to grab the path for open file and use that instead. We have fan dipoles and who knows what else we have in here. G5 RVs, horizontal loops, all kinds of things here. I don't know what a fan dipole is. I should probably checked it first. Here they've literally decided not to use symbols. They're going to do every measurement in feet, and their geometry simply says 6 feet to the left here with this and that, and it created an antenna that looked like this one out of multiple wires. Doesn't look like they have a ground. But maybe that's what you want, a butterfly antenna. We'll go ahead and look at a far field. They're running it on 10 megahertz. So everything is in feet and size for 10 megahertz. And you can run it and try and get some, it's a fan dipole center, and get some answers that way. Look, I think I've used a good amount of time here for today. I'll entertain any more hands raising. You know, I encourage you to play around with these tools, maybe try and follow some of the examples that you're finding, explore at will. There's, like I say, there's a ton there in that models folder, HF beams, collinears, all kinds of things. 3-element inverted V's. Who knows what it looks like? Oh, that looks like the one that was up on the roof of that house. Okay, and it has a ground. And they're going to run it for 7 megahertz. So 40 meters. I heard a ding, but I didn't see where the answer went. Ah, here it is. Oh yeah, look at that. They got almost 12 dB of gain just by putting 2 extra pieces of passive wire on their roof along with their inverted V. Not bad. What does that look like in 3D? Like this. And anyway, you can spend hours enjoying the fun.
Yeah.
There you
How do
go.
they turn the house?
There you go.
Just got to be lucky your house is built in the right direction.
I'm not hearing too many more questions. So with that, John, I'll turn it back to you for any concluding remarks. But I want to thank everybody who participated in tonight's TechNet. Hope you learned something out of it. If not, at least you've been exposed to what this antenna modeling, and for me, climbing around on the roofs and moving wires around and stuff up there, that would be a real chore. I would rather get close by trying it a few times in the computer first before going up and down in the trees and doing everything else that I wanted to do. And I hope now you have this tool in your toolbox available to you as well.
Tim, that's terrific. This is exactly what I was hoping for. I mean, when everybody can fool around with this on their own desktops and play around and cheat the way Mark did, you can, either that or with a hell of a lucky guess to 5 decimal places, Mark. Uh, So, looks like the recording is probably working. I forget who promised to, take these things and put them out on Zoom. I know we haven't been doing that lately, but we do have all the recordings. I think it was Doug. I will go back and confirm that. We definitely want this on Zoom because I think it was terrific. We don't have a topic for next month. We'll dream something up if you have suggestions. I know we've had a lot of discussion, last month, both early and then later with just Mark and myself. So if you have ideas, let me know. Otherwise, we may try and stick with antennas just because we're talking about it for these 2 months. I did ask, by the way, I emailed Spencer to see whether he'd be willing to do either a Tech Saturday or a TechNet with us. So basically for, just a Q&A session, which I think a lot of people would love to just be able to sit down with that guy and start asking him questions. I have not heard back from him, but that's a possibility. So thanks, Jim. Thanks to everybody else, and we'll see you guys next month or before that.
All right.
Night, everybody.
73.
Thank you.
Bye.